Thanks for joining me today as we take an inside look at what it's like to work at a Canadian consulting engineering company. On this episode, we're talking about structural engineering and building high-efficiency buildings. My name is Graham, and welcome to another episode of AE Live.
Coming to you on the internet audio, all the STEM homies know ways where you gotta go vibing your ride to the Graham and Michael groove. Whoa, it's a whole new funky flow and treat your ears, get the gist of careers from the list by engineers and scientists, maybe twisted up with technologists. The podcast, baby, and not to be missed. Got more fly than a ripe banana, like Sam, I got the stamina streaming across Canada. I can treat sugar band, I got that swiggity swag, yeah, and the 411 from Whitehorse to Niagara. Don't you know we're gonna innovate? Got a topic here to elevate. Gonna entertain and educate.
This podcast is recorded in Vancouver on the traditional, ancestral, and unceded territories of the Coast Salish peoples, including the Musqueam, Squamish, and Tsleil-Waututh nations. Our world is increasingly aware of the need to be conscious of climate change. Canada is one of 120 countries that are committed to being net zero by 2050, and we're going to explore a little about what that looks like from a buildings engineering point of view. Joining me today will be Jermyn Wong, a structural engineer with Associated Engineering. He'll talk about his experiences using engineered wood and on working with high-efficiency projects, including 2 residences built at Simon Fraser University in Burnaby, British Columbia. It's exciting to see projects that take a low-carbon, high-efficiency approach. The Unisphere, built in Silver Spring, Maryland, is a 210,000 square foot commercial building and the largest site-powered net zero building in the United States. The building includes multiple sustainability strategies, including photovoltaic panels, a concrete maze beneath the structure to provide natural ventilation, and geo-exchange wells that go 500 feet down to provide geothermal energy. I'm joined now by Jermyn Wong. Jermyn completed his master's degree in structural engineering in 2010 and has been part of some complex, iconic, and award-winning projects over the last 2 decades. Jermyn's interest in sustainable design and expertise in engineered wood has involved him in the Greenbrier Residential Development and the Wood Innovation Design Center in Prince George, the tallest wood-framed building in North America. Jermyn, you have an impressive collection of projects under your belt. Thank you for spending some time with us today.
Thanks for having me.
You're a building structures engineer. Tell me a bit about what that means and what inspired you that area of interest.
I'm a structural engineer, so I'm involved in the design of building structures. And the structure of a building is usually a fairly important part of the building, obviously, right? It keeps it safe. It helps it resist environmental loads, whether it be the self-weight of the building, but also occupancy loads, environmental loads like wind loads, snow loads, earthquake loads, and so on and so forth. And then when you design a building structure, you don't just design the part that's visible. A lot of times the structure is hidden by the finishes, nice cladding. Now in terms of how I got inspired to be a structural engineer, I always enjoyed physics when I was young. And I was inspired by my older brother, who at the time was already a practicing architect. And we would visit buildings together when we were traveling. And I became increasingly interested in architectural buildings. So when I was finishing my undergrad, my goal was to become involved in the design of architectural buildings and to be able to work on something tangible, perhaps even iconic, I would say.
Are there any particular features that really jumped out at you as being interesting or that made a building iconic?
I would say it's the ability to celebrate or expose parts of the structure without having to hide it. For example, in a lot of conventional buildings, people think that the structure is the ugly part of the building, the columns, the beams, and you want to hide it up as much as you can. But in reality, when you have in some situations, it actually makes sense to be honest about it and to detail it well so that it can be exposed. And I want to use the word celebrate it, right?
That's great. That's really interesting insight into the way kind of you look at a building. So you joined Associated Engineering 2011. What projects kind of have you found memorable in those first decade here?
So some of the more notable projects that I've been involved in since joining Associated They include the Jericho Reservoir, where we specified sloped exterior concrete walls, as well as a form liner for the concrete in order to mimic the texture of glaciers, to add visual interest to the structure so that it would integrate better with the community. Another example was the Powell River wastewater treatment plant, where we introduced some exposed timber elements to add warmth to the facility and make it a little bit less of an austere plant environment. And we also designed some green roofs on some of the buildings in order to kind of reduce the visual impact to the neighborhood. And then another notable project was the Kinsman Park miniature train station at a small amusement park in Saskatoon, where we designed a cross-laminated timber roof structure that's supported on metal-clad walls and architectural precast columns. And the roof structure actually was a hybrid roof structure comprising cross-laminated timber panels and concealed structural steel elements. So that was really interesting, and it actually won a landscape architecture award. Another interesting project was a special private residence on Bainbridge Island in Washington State. And that project was actually a huge experiment for us to explore the use of different innovative materials to try to lower the carbon footprint and energy consumption of the building. So besides conventional wood framing and concrete, we also introduced reinforced rammed earth, heavy timber, and prefabricated wood insulated panels. And then one other project that was pretty memorable was the Tuason First Nation sewage treatment plant, where we deliberately specified cross-laminated timber walls for the upper stories of some of the buildings to not only lower the seismic weight, but to also improve the corrosion resistance against the vapors from the processes.
Tell me a bit more about the Bainbridge Island project there. You're getting to work on a private residence and in many ways just experimenting with things you want to do. That seems like a unique project to be able to put into one's career.
Yes, that project was actually commissioned by Jason McLennan, the founder of the Living Building Challenge. So it only makes sense for him when he wanted to commission the design and construction of his own house to use it as a platform to perform an experiment and explore with all these options out there, right? So, like I said, there's a combination of many different techniques, not just on the structural side, but in the other realms as well, mechanical, electrical, trying to reuse water, etc., etc. But the structure itself was also pretty interesting.
Mm-hmm. Right. Did you learn anything kind of unique or unexpected that you weren't expecting to get from that?
Like I said, it's an experiment, right? So it may not be the most cost effective because we're trying to explore what the possibilities are. So in a lot of ways, we're pushing boundaries, right? It was, in the end, it was still a success. Yeah. It was a pretty spectacular building.
You also mentioned putting like a green roof in building. I think that's something we've seen increasingly get used in a lot of, I guess, iconic buildings. What goes into building a green roof?
The purpose of having green roofs, it serves a number of functions. For example, it helps control roof runoff and rainwater to a certain extent. And it also can make buildings look nicer, especially when, you have an industrial building or some kind of an infrastructure building right in the vicinity of residential areas, and you're looking down from those residences, and it makes it look better. It helps integrate it to the community. So more recently, I guess we've done that on a number of projects, including the Barnston Pump Station in Maple Ridge or Pitt Meadows, but also the Powell River wastewater treatment plant. And you not only have to coordinate with the suppliers of the green roof suppliers to address the details or the attachments to the primary structure, you also have to review the loading that's imposed on your roof structure. And you have to make sure that your structure can support it, has the right backing or stiffening or strengthening in order to allow the attachment to happen. And on steeper slope roofs, we have to also consider the sliding load or the slipping of the green roof by introducing additional elements that would restrain the roof from slipping off. So there are a multitude of considerations.
All right. I wanted to come back to you mentioned exposed timber. I think you mentioned that specifically in Powell River, but I know you've done exposed timber work in various other projects. You've done some interesting things with wood across multiple projects. Tell me a bit about what cross-laminated timber is and engineered wood, and why, how that's used in a project that you've been on.
So there are different types of engineered wood. So normally when we build conventional wood frame houses, it's just dimensional lumber. But engineered wood is basically wood products that are made from some kind of manufacturing process. So it allows for longer, larger, and stronger materials. So glued laminated timber is just one of the examples. These products are mainly used for beams or columns or other components. But there's also mass timber, which is walls or panel products. And one of the key examples or a recent innovation is cross-laminated timber, where you take pieces of dimensional lumber and you lay them flat, and then you put your next layer, but you rotate the orientation and you put them on. And then you rotate the next layer again 90 degrees and you put them on. And then you have multiple layers of these lumber pieces, and you press and glue them together in the controlled environment into panels that now can span as floor slabs or upright wall panels and so on and so forth.
Great, thanks for that explanation. It really helps. You've worked on two of the tallest wood structures in Canada.
So in terms of tall wood buildings, we were fortunate to be the owner's engineer on the Wood Innovation Design Center in Prince George, which actually is the campus for UNBC up in Prince George. And the key thing with working with engineered wood is that you have to do a lot of pre-coordination with other disciplines in order to maximize the amount of prefabrication so that you can shorten the site installation time. So that will help you that will allow the project to be more successful. One of the key purposes of using these mass timber products that are prefabricated is to increase the amount of prefabrication in a controlled environment so that you can shorten the site installation time. Another challenge with working with these mass timber products is that you need to be always aware of the supply chain implications, the manufacturer fabrication capabilities.
So it's a bit more management time, you think, but you kind of see those savings in construction and on-site?
Yes, there is more. You have to do more work, yes, early on in the project. You have to understand what the availabilities are for these types of products, capabilities, like I said, and then definitely more coordination. If you plan for those things ahead of time, it will allow for more repetition of the manufacturing of the elements, and then which also leads to better cost effectiveness and quicker construction.
So the innovations that have come about in terms of engineered wood, what options does that give you that traditional cut wood wouldn't give you when you're talking about building a building structure?
With traditional types of lumber, dimensional lumber, you're limited to certain lengths and sizes. So, for example, for our residential single-family houses, it's built out of stud walls and joists, and at the most, maybe trusses. But with mass timber or engineered wood or glulam beams, you can have large spans. You can have quick repetition, quicker site installation time. You can have larger scale structures using these products.
That covers a lot of the projects you've worked on over the years. You've been with Associated now for 15 years. how would you say your approach on a project has changed over time?
So I started my structural engineering career in 2006. So now I guess it's been 17 years, and I've been privileged to be able to be involved in a wide range of projects, ranging from iconic community centers, visitor centers, large reservoirs, water treatment plants, and so on and so forth. And they're all unique in different ways. So now that I have acquired more experience, I am actually becoming more aware of the importance of meeting many emerging needs on projects. And I'm becoming increasingly interested in developing holistic structural solutions on projects. So to give you some examples, right? Um, some of the considerations include constructability, cost effectiveness, the operations of the building, the carbon footprint and energy efficiency of the building, but also the aesthetics. So how do you balance all of these different factors and try to address each one? On the SFE Parcel 21 residences, we had to come up with structural solutions to address multiple challenges. For example, preserving the continuity of the thermal insulation, reducing the amount of thermal losses and thermal bridging at different points of the building, uh, mitigating the effects of vertical wood shrinkage of the building, and then the high seismicity of the location, and also the varying floor plans at the different levels of the building, which also led to some challenges. And then on another project, the Jericho Reservoir, um, how do you add visual interest to an otherwise straightforward kind of tank or box, right? In order to make it integrate better with the neighborhood, right? While maintaining functional requirements such as water tightness of the reservoir, continued operability of the reservoir, and post-disaster resilience. So on the Powell River wastewater treatment plant, not only did we have to address the needs of the community by reducing the visual impact of the facility, it's also important to coordinate the design with all the other critical disciplines in order to design such a facility successfully. So those other disciplines included the processes, the mechanical and electrical systems. So, and then recently on the Chestnut Way Reservoir Seismic Retrofit Project in Port Moody, uh, we needed to address multiple challenges. We wanted to minimize the disruption to the continued operation of the reservoir. So, and we also wanted to not alter the gravity load path and behavior of the existing structure, nor inadvertently impose any restraint on the existing structure and its ability to accommodate thermal expansion and contraction. So we ended up designing these exterior structural steel plate components that were anchored to the exterior of the reservoir as part of the seismic retrofit solution.
So when you look at your career and incorporating these more holistic solutions to your projects, you're a student going through your education, learning the very technical aspects of engineering and maybe anticipating coordinating with other engineering disciplines on a project. But was that idea of problem solving for community needs brought up as much, or is that something that as you kind of go through your career, you realize that the importance of, I guess, of consulting with the community, of addressing their needs and making something that doesn't impact the communities as much as just digging a hole in the ground and redoing things?
That's a great question, because you're absolutely right? A lot of things aren't taught in school. So when I was doing my undergrad or even my master's, it wasn't just technical knowledge or structural knowledge. There were also other courses on environmental engineering, project management, project economics, and stuff like that. But they were all kind of in separate silos, and they didn't give you a roadmap. So a lot of these skills were kind of acquired through experience. And now, as I enter my 18th year of my career, I am still learning, right? I'm still learning all the time. I don't know everything yet, In fact, I don't know much at all, right? And you're absolutely right. There are many considerations. We have to work with the communities. We have to work with the clients. We have to work with all the other stakeholders. We have to understand what the important considerations are and try to balance it so that we can have a successful project. Right? Cost is important, but it's not the only measure. There is a variety of other things to consider. So how do you optimize that? Right? That's not just a skill, but in some ways possibly an art in some cases.
Let's dive into SFU and Parcel 21. That's a pretty recent project and a pretty giant project that you've been involved in. You were looking to meet some pretty stringent energy use restrictions. Can you tell us a bit more about it?
So the SFU Parcel 21 project originally targeted passive house requirements, and then because of certain budgetary constraints, it was relaxed a little bit, but it was still targeting high performance requirements. And in order to allow that to happen, not only did the mechanical and electrical systems and so on and so forth have to be efficient, but obviously the architectural and structural design also needed to accommodate or be detailed so that it would enable this high performance. And some of the key requirements to achieving good energy performance on a building include preserving the continuity of the air barrier and thermal insulation, and minimizing thermal losses and thermal bridging at the different interfaces of the building. So the SFE Parcel 21 project, it comprises, I think, 90 affordable units for master students and their families at SFU. And there's a 6-story wood frame building, and there's a 4-story wood frame building, and then there's a concrete parquet underneath with some common space and a pavilion building that's kind of a shared amenity and some playground space as well. So on this particular project, we had to detail the exterior walls with outboard insulation in order to help preserve the continuity of the thermal envelope. We also had to detail the residential building interface with the concrete parquet or the concrete foundations. There are several different interfaces where there could be a thermal leak or loss, or we call it thermal bridging. And we had to detail all those connection points carefully in order to minimize those losses and effects. And then thirdly, there were a lot of sunshades and canopies and other appendages that were added for various reasons. So, for example, there were entrance canopies that would allow provide a rain shelter for people at the entrance of the building, but there are also these sunshades that would help provide some cooling against the westerly sun. And oftentimes on conventional buildings, when you build these appendages, if you don't detail them well, then you get a lot of, again, thermal bridging at those connections.
From a owner, operator, occupant point of view, you've done all of these measures to make to reduce thermal leakage in your words and to protect the building from its to minimize energy use. What is your average person standing in the building feeling? Is it noticeable? Does the building have a different feel than something more traditional construction?
That's a good question. It's hard to say for sure because comfort is it may vary for different people. But generally speaking, if you're in a conventional building with conventional systems or maybe less modern systems, you may get more like swings in temperatures or hot spots or cold spots near the window, for example, or draft from the air conditioning or the HVAC systems and so on and so forth, right? But in this type of high performance building or high performance project where we select efficient HVAC systems, but also detail the envelope to be fairly airtight and thermally continuous, you get far less of this swing or draft or all these other effects. It's far easier to maintain a consistent condition or consistent environment. There are studies out there that where they use these they measure the temperatures at different surfaces of buildings, and with conventional buildings, you get way more variability with high temperatures on surfaces exposed to solar radiation and whatnot or stuff like that. Right? Whereas with this type of high performance building, you see far less variability. So you won't have like warm rooms and suddenly a room where you're freezing, and then it's just going to be way more controlled and consistent. I think to me it's way more comfortable.
Is there something about the SFU residences and the project that you're most proud of?
So we are very proud to be part of this innovative project. We were able to design a structure that responded to multiple challenges. So first of all, the key challenge was the high performance requirements of the building, but there were other challenges as well. We needed to, for example, detail the structure to mitigate the effects of vertical wood shrinkage, especially on this type of mid-rise building. Mid-rise wood building is defined as wood buildings that are maybe more than 4 or 5 stories tall, where the cumulative effects of shrinkage of wood start to matter more. On conventional, say, single-family houses where you only have like 2 stories or 3 stories, that cumulative effect, even when it adds up, isn't that much, right? But if each level shrinks by a certain amount and things want to move down, and you have a 6-story building, it starts to matter, and then your detailing has to be carefully considered to avoid damaging or causing some kind of restraint or other negative effects. So another challenge on this project that we managed to address was laying out a good seismic resisting system, which was actually made more difficult by a couple of factors. First of all, the windows on the perimeter walls were kind of offset from each other from level to level to create visual interest and a nicer architectural appearance. But that actually made it more difficult to develop a proper seismic resisting system. Another factor that contributed to the challenge was the varying floor plans and layouts for the individual units at different levels of the buildings. But we managed to develop the solutions to that, and we ended up with this fairly successful building. So we're really proud to be part of this project. The project actually won 2 awards. The first one was the Net Zero Energy Ready Challenge, which is a provincial incentive program for large buildings targeting high performance. And the SFU project was recognized as one of 11 winning projects out of over, I think, 50 submissions or applications. And then more recently, our SFU project won a second award, which was the Sustainable Architectural and Building Magazine's Canadian Green Building 2023 Award in the large residential category.
Great. Congratulations.
Thank you.
Has this been your first experience with kind of passive house net zero? I guess you did some of that with the Bainbridge Island project, but
Yes, that would be my first project of this scale. 90 units and 2 fairly large buildings, and then the construction value was nearly maybe 25 million or more than that. So it's quite a significant scale.
So that experience on something that is meeting those kind of high performance standards, does that inspire you to try and chase more of those buildings?
We are interested in working on more high performance buildings. I guess from the SFU project, we gained some experience. We have the skill set within our team. We have structural engineers, mechanical, electrical engineers. We also have energy modelers that can do energy modeling, and we have BIM specialists that can create models. So we have the skill set to work on and deliver successfully on this type of project on high performance buildings in general. It should also be noted that it's going to become increasingly important to be able to design high performance buildings because the codes and regulations, they're starting to adopt more stringent requirements, and it's only a matter of time before higher energy performance will become mandatory. So it's not only whether we want to work on it, but it's also becoming a necessity with time.
Is the change, and I guess the push to have more buildings be high performance, being driven primarily by code changes and requirements from that end and government regulation, or do you see developers thinking that I'm going to make these changes because by the time my building's ready and by the time I'm starting to get occupants for it, the cost savings of high performance buildings is worth it?
That's a good question. It depends on the type of owner or client. I guess for private developers, more often they need to look at financing and the initial cost, especially depending on how long the ownership phase is, right? And then, but when you have government clients or other types of clients, it varies. It can become a larger factor for those types of sectors or clients. I would say it does vary from sector to sector.
Do you see yourself being involved in mentorship in terms of engineering and young engineers here at the company?
So throughout my 17 years of my career, I'm happy to have been able to be involved in the design of many interesting projects. At this stage of my career, I would say that my main goal is to continue to make a difference, not just doing my work or leading projects or designing successful projects, but also mentoring young engineers and guiding them and helping them succeed. So I've been doing that for a number of years now as the discipline lead of building structural at Associated, and I'll continue to do so and to act as this go-to person for team members and junior engineers. But outside of work, I also would like to make a difference, and I've been involved through other avenues. For example, I'm one of the EGBC registration interviewers for structural candidates who apply for their PNGs or apply from overseas. I am also one of the examiners for the BC Building Codes and Practices exam. And then I was also one of the co-instructors for the Heavy Timber and Mass Timber Design course with SEABC. I want to be able to not only provide mentorship, but also sort of give back to this profession.
Great. That's really great. Thank you for sitting with us for this last while and answering the questions. Any kind of last thoughts about where your career has gone and what you're most proud of?
I would say structural engineering is a rewarding career. I've had a fun time. You get to solve problems. You get to do something that's tangible, that you can be proud of. I'm happy to have been involved in many projects. Overall, it's been quite a ride.
I think that's great.
Thanks for your time. Yeah.
That was Jermyn Wong, Building Structural Division Lead at Associated Engineering. He joined me today to talk about some of the interesting projects he's been involved in over the last 17 years and his passion for using a building's structural elements in unique and beautiful ways. Jermyn also spoke about his role on Parcel 21, a pair of high-efficiency residences at Simon Fraser University, and the challenges they faced on that project. So what exactly determines a high-efficiency or zero-carbon building? And who sets that standard? Well, in 2017, the Canada Green Building Council established the first dedicated zero-carbon building standard. One of the pilot projects to demonstrate this new standard was the Joyce Centre for Partnership and Innovation at Mohawk College in Southern Ontario. This was the first building in Canada to receive certification in both design and performance. The building maximizes its high-performance building envelope and minimizes heating and cooling demand, in part by using an all-electric geo-exchange system and a rooftop photovoltaic system. At just under 9,000 square meters, the building produced 115% of its energy use over the course of 2019. I hope you've enjoyed today's discussion about structural engineering, whether we're talking about community centers, water treatment plants, reservoirs, private homes, or miniature train stations in a public park. They all provide a structural engineer an opportunity to build something unique and maybe even iconic. Thanks for joining me today on this episode of AE Live. I'm your host, Graham Nix. Tune in next time.
Coming to you on the internet audio, all the STEM homies know is where you gotta go vibing your ride to the Graham and Michael groove. Whoa, it's a whole new funky flow and treat your ears, get the gist of careers from the list by engineers and scientists, maybe twisted up with technologists. The podcast, baby, and not to be missed. Got more fly than a ripe banana. Like Sam, I got the stamina streaming across Canada. I can treat sugar band, I got that swiggity swag, yeah, and the 411 from Light Horse to Niagara. Don't you know we're gonna innovate? Got a topic here to elevate. Gonna entertain and educate.